For this lab, you're going to investigate how does the force that you apply to an object affect its acceleration. So what we're going to use is a track on a low, or a cart on a low friction track. If you can see, let me pull it up a little bit further. I have a mass hanging down the other end there. There's a string. I know it's fishing line, so it's difficult to see in the video. There's a string that connects the mass over a pulley to my cart here. So I hang masses on the other side. That provides a force, which then makes the entire setup accelerate the entire system. We'll talk about whenever you have multiple objects at a later point, but here it still works. In other words, if you have a cart and a mass hanging down, the force of gravity is what's actually pulling the mass down. So likewise, string all the way connected, whatever the force of gravity is on that mass is providing your force. Force of gravity on that mass is what your force is going to be. So whenever you're choosing your independent variables, you actually need to look at masses. Masses that you should choose. Please pick small ones. For example, I have two 20s and a 50 that I'm going to use in combinations. If I were doing this right now, maybe 20, 40, 50, 70, and 90 grams would be what I ended up choosing. Notice grams, not kilograms, whenever I gave those numbers, so make sure to convert if you choose to go with those or any others, because all of our mass sets are listed in grams, because a kilogram is actually a decent amount of mass, especially when doing something relatively small like this. Now, setup. You have magnetic stoppers on both ends. You have feet on the bottom, feet to make sure that you can level out the track, because you don't want any component of gravity doing the accelerating. You only want the hanging mass at the end. So if I took that mass off at the very end, I'd make sure the cart didn't roll on its own because of gravity. Run the string through a little hole right there in the magnetic stopper and over a pulley down there. On the other end, pulley right here, hanging mass down at the very bottom. All right. Now, what I'm doing with the masses, let's talk about that idea of the setup. Any of the masses that you are going to use needs to either be hanging down there or hanging or on the cart itself. The total mass of the system should not change. Write down, control variables, what the total mass of the system actually is. Make sure to include the cart's mass. Okay, make sure to include the cart's mass. Here, I only have 3 masses. Now I'm going to change my force by changing which masses are hanging down there, right? But the total mass remains the same. In other words, right now I have 20 grams down there, 0.02 kilograms times about 10, 9.81, so about 0.2 newtons, right? Is what's doing the pulling on this cart right here. If I want to change it to 0.4 newtons, I just simply take the other 20 out of the cart and I'd go hang it down there with the other one, right? And so now I'm up to 40 grams, 0.4 newtons, it would do the pulling. If I wanted to change it to 0.5 newtons, I'd grab my 50 gram, I'd go hang it, I'd take the 20 and I'd put it back in the cart there. So you don't actually have to have 5 masses to do this. You probably only need 3, but if you want to use 5, you'd be fine. But 3 should be enough. You can then do things in combination. All right, now, if you think about what you're trying to get to, in the end, I want to actually get to this idea, quickly sketched out on a whiteboard, of force and acceleration. Force is my independent variable, acceleration as my dependent variable. Now, if you so choose to graph these two backwards to where you put force on the y and acceleration on the x, that's actually fine and might make your data analysis even a little bit easier whenever you're doing it out. But for now, we'll graph it out like this, where independence on the x, dependence on the y. Presentation table. Here's the thing. The force, while it's an indirect measurement based upon the mass, right? Mass, force of gravity equals mass times 9.81. That's pretty straightforward. You can just do all of that on your raw data table, right? You can do those calculations quickly ahead of time. Those are your independent variables, those forces. Life is fine. But acceleration, that is not a direct measurement either. That is an indirect measurement. We actually went over how to do this in a previous lab, but it requires a few other steps. Specifically, you're going to need a calculations table where you're going to use a kinematic. So maybe I put my forces in the first column over here. Only reason that I end up having force in the first column is that way it just simply identifies independent variable goes with this stuff. Set a displacement. Choose a displacement on your track that you're going to let the cart move. The initial velocity should be 0. You're going to need to time how long it takes the cart to move that displacement. That will allow you to calculate acceleration. Show one example calculation. Let's talk about setting your displacement. Make sure that you do not choose a displacement that is too far. So the little mass hanging down there touches the floor at some point. If I let it touch whenever it touches the floor, which is right here for me in my cart, almost at the end but not all the way, there's no longer any force being applied. I can pull it all the way back up and get the mass almost all the way to the pulley, but it looks like I still have a little bit of a gap right here. So to choose my displacement, I need to make sure that I actually do my setup first to try to see what range of value, what displacement I can choose, what range for my displacement can I choose that won't end up letting the mass touch the floor on the other end and won't pull the mass over the pulley whenever I have it all the way back. So raw data table is going to be all about time, right? Because you're letting your displacement be constant. So you have your forces listed out, and then you'll do try 1, 2, 3, 4, 5, right? Average all of those times. That'll let you then substitute into your calculations table and get all the way around to acceleration and graph it out. And obviously, the force acceleration graph is going to have meaning. That meaning is going to come in the slope, and you should be able to get the meaning should be you should be able to end up getting to the mass. The mass of the system that will let you look at accuracy. You can even do a percent error calculation with the mass because the mass is known as one of the control variables. Let's see here, other thoughts that I need to give you. I can't think of any right off the top of my head. Make sure that, like I said, you keep the total mass of the system the same. If it's not hanging down there, it's in the cart.